All right. So we are continuing our quest of equilibrium. It's going to be going on for a lot longer. Okay. I mean, a lot longer. And today, I always do that. Today, we're going to look at solubility equilibria. Okay. So we're going to have a new K constant. It's going to be KSP. And it is a solubility product constant. SP, solubility product constant. All right, let me share my screen. And you should have the questions that I will be referencing here, okay? Put this over there real quick. Let me get my call away. Oh, I gotta share my screen here. Oops. And now I can share my screen here. You doing all right? Calculator. Probably need a periodic table today too. All right. And let me get here. That's your worksheet. We need to go to our notes. And those are practice problems. Oh, I need to go up here. All right, so we are talking about solubility equilibria. Students have a hard time with this, all right? Just because they get terms confused, and I understand, so I'm going to try to help you with that. Now, KSP is the solubility product constant. But as I sit here, I realize you're still like, what are we talking about? We are talking about insoluble salts, okay? Salts that are said to be insoluble. So that when you put those salts in water, they do not dissolve, right? However, what is actually the case is that a very few amount of the cations and the anions are in the solution, right? But very few. But they are actually there. Right, so what we've had is we have had some slight dissociation, right? We have experienced a slight bit of slight dissociation of salt. Remember, salt is an ionic compound. Because there's a slight dissociation, what we have is an equilibrium system. And as some ions are ionizing, they're constantly going back to the solid, right? It's just the rate is constant so that the concentrations are constant. This process requires a dissociation equation. And I think a lot of students fail to realize that. So what we have here is a salt in equilibrium with its aqueous solution of ions, okay? And I hope I'm not making this sound too hard. I'm trying to help you to realize how simple this is. So it will always be a salt, solid, in equilibrium with the cation, right? The aqueous cation and the aqueous anion. And that's your generic dissociation equation, right? Okay. So for example, and these are for insoluble salts, salts that are said to not dissolve. Aluminum phosphate, right? When you put aluminum phosphate in water, it doesn't dissolve. However, aluminum phosphate has a KSP value, which reveals the magnitude of which, let me write that, the magnitude, that means how high or low, of a salt's KSP value reveals the extent to which it dissociates, right? All of this stuff you should realize. And I'm going slow because you got to understand it, right? So the greater the KSP, the greater the percent dissociation. Okay. All right. That works. That works. I'm going to say in water just because. All right. Okay. Now, KSP and solubility are different things. And I think that's why students get confused. Solubility, we're going to use an S for that, okay? We will use ice charts. We will use S's as opposed to X's. You can use whatever you want. You can use X, Y, Z. But typically we use S's, and it helps you to remember that whatever that value is, X is S, S is X. And for KSP problems, it is a solubility. And it is in moles per liter, or sometimes, guys, it's in grams per liter, okay? But in an equilibrium expression, it is concentration in moles per liter. Now, let's continue before we get to our first practice problem. Let's have the salt that we referenced, aluminum 3, 5. Let's start simple. Let's start simple, okay? Let's have a 1-to-1 ratio. So let's say barium. I hate it when that happens. And I'm going to get a different color. Let's say that we've got barium oxide as a solid, and we put it in water, but it really doesn't dissolve. However, some of the barium ions dissociate. Right, here's our dissociation equation, like you're writing net ionic, complete ionic equations, but we have a double arrow and our 2 negative. All right, now, when I write my KSP for this, it is simply BA concentration of the ions times O2 negative concentration of the ions. Remember, this salt does not go, right? It will not be, the amount that is there will not be present, all right? This salt will dissociate to a particular extent in a certain amount of water at a given temperature. Its K value will tell us that. I can now know the concentration of these and solve for K, or I could know K and solve for the concentration of these. I can also predict if I will have a precipitate, right? This solid is my precipitate, right? When ions come together to form a solid, I have a precipitate. So if Q is greater than KSP, then the reaction shifts towards the left. It shifts towards the solid. And more precipitate or a precipitate forms. So either we form it or we form more of it, right? Right? Because it's already there, but we cause more solid to be present, right? If Q is less than KSP, then the reaction will go this way and more salt will dissolve. All of this is pH dependent sometimes, and we're going to get into that. Okay, we're also going to be able to say, yes, a precipitate will form, or no, a precipitate will not form. Now, I'm going to erase this because I need to, because my practice problems are creeping up on me. Now, what I can do actually is I can move them down, because I want to say a few more things before we get started on practice problems. What do I want to say? So I want to look at this equation here, right? So KSP here equals S times S, and that is S squared. All right, let's look at another one. Let's go, trying to think of one that actually does not dissolve, that has a 1-to-2 or a 2-to-1 ratio. All right, PbO2 is a salt that would not be very soluble. However, some of it would dissociate. That's actually a 4+, guys. If you want to figure that out, that would be a 4+. All right. And now let's look at this here. KS. Well, let me go about it a different way. Okay. Let me go about it a different way. When this dissolves, won't it be plus S plus 2S? Where if I can clarify that up here and do the same thing for my barium oxide, right? When it dissolves, won't in your ice chart it be plus S, right? Plus S, plus S. So down here, I want you to notice that I have an S and a 2S. So watch this, KSP, it will equal the concentration of lead-4 ions multiplied by the concentration of oxide ions squared. However, we also know that this will be S and this will be 2S, and it is also squared. So what I have is S times 4S squared, and that equals 4S cubed. And this time I would solve for KSP this way, where up here you see that my KSP is equal to S squared. So you've got to pay attention to the ratio of cation to anion. And for that reason, I cannot compare this value with this value to predict S, my solubility. Okay? My molar solubility, the amount that is present. I can say that one, simple as that. It is as simple as that. S equals molar solubility. We wrote it down. S, molar solubility. KSP values can not predict relative solubilities, molar solubilities, unless the ratio of cation to anion is the same. All right, let's just jump into some problems here, okay? And let me move this down because we're gonna need more room. And we'll just take a slow approach, baby steps, all is well. Okay, so we're going to calculate KSP from molar solubility. A certain temperature, the molar solubility of the salt M2X2 is found to be. Okay, so my dissociation equation, my salt will have the formula MX. All right, that will be my solid. It's only slightly soluble as evident by its -6 KSP value. it will dissociate into cations and anions. And I need to calculate KSP. Notice, guys, that KSP will be equal to the concentration of this at equilibrium and the concentration of this at equilibrium. The solid is not a factor here. I do not need to even know how much solid I have. It doesn't matter. It doesn't matter. Only a certain amount will be dissolved in a given amount of solution, right? In a 1 liter solution. So what I hear though, right, is, so let's go here. I'm not really, I can have an I, but that's 0, okay? I don't know how much MX I have. I don't need to know. I know the change will be plus S, and I know at equilibrium, this will be S and this will be S. So a lot of times what you'll see is just a big X drawn through there. It's not a factor. It doesn't participate in the equilibrium, okay? Its concentration doesn't change. Okay. Hold on. So what we have here is KSP equals S times S. So we know that KSP equals S squared. S is the molar solubility. So that is given to us in our problem. We have a molar solubility. S equals 4.15 times 10 to the negative 6. So KSP equals 4.15 times 10 to the negative 6th, and that needs to be squared. Right, I actually have that value right here. 1.72 times 10 to the negative 11th. Okay, so we were given molar solubility. We solved for KSP. We made sure to recognize whether we needed to multiply that molar solubility by a value or not. And since it was 1-to-1, we did not. Okay, so not very soluble. Some of these exponents will be in the 20s, 30s. So you get some very, very low numbers here. Oh, we got another question. That was 1. Let's look at 2. Let's calculate KSP from a grams per liter. All right. At a certain temperature, the solubility of, calcium sulfate, all right, S is found to be 0.66 grams per liter. We need to calculate KSP. I know that KSP, this is going to be calcium 2 plus, sulfate 2 negative, still a 1-to-1, right? So this will be plus S. This will be plus S. KSP will be equal to calcium's concentration, whatever we define it to be, sulfate's concentration, whatever we define it to be. We have defined it to be an S and an S. So KSP equals, once again, S squared. S needs to be in moles per liter. So we need to come over here and convert our 0.66 grams per liter to moles per liter. Grams of what? Calcium sulfate. The molar mass, guys, for calcium sulfate is 136.1. And that will give us a molar solubility of 4.85 to the negative 3rd. All right, so that is equal to S, because that is a molar solubility, and that is S. Therefore, KSP equals 4.85 times 10 to the negative 3rd squared, and that's going to be 2.36 times 10 to the negative 5th. Is your KSP value. Now, because these two salts are both in a ratio of 1-to-1, right? The cation to anion, we have a 1-to-1 ratio. I can compare my KSP values and what I should expect to see, and I'm not looking yet, and if I'm wrong, then I have to end the video. What I expect to see is, because this KSP is higher, I expect to look up and see a molar solubility that is greater. And I do. Okay, higher, therefore greater molar solubility. But recall, I could only compare those two KSPs because the ratio of cation to anion was identical. Otherwise, I could not compare them, right? But I do see, in fact, that calcium sulfate's solubility here was greater than whatever salt this was is solubility here, which was to the -6th. Okay. All right. Let's go on to the next problem. Calculate molar solubility and solubility in grams per liters from KSP. Given, okay, so I see that we're dealing with silver sulfate. Go ahead. As soon as I see KSP, as soon as you see KSP, probably want to think about that dissociation equation. Remember, we don't need to deal with the, I'm not going to write what KSP equals yet, right? Well, I'll write KSP equals, but I make sure you pause for that. Well, it'll be whatever we have defined the silver ion concentration to be squared over whatever we have defined this concentration to be. That's what I need you to realize. Let's look up here. We also know what KSP is. It's 1.41 times 10 to the -5th. So I cannot compare this KP to, or KSP to the other guys, right? I can't do that because there's not a 1-to-1 ratio. So I can't assume that the molar solubility here is in any way related to this. I don't know. Unless you're really good at math in your head. I'm not. Okay, and we need to know the molar solubility. So that means, what does S equal? Okay. All right. Well, let's go to our ice chart. I don't usually write all this out for KSP, but there is none of this initially. We will gain 2S. We will gain 1S. At equilibrium, this will be 2S. And at equilibrium, this will be S. That goes there, and that goes there. All right. So you may see that more quickly than others and maybe be able to bypass a few steps. That's kind of up to you. Not a big deal. Nothing's taking long. Let's plug those in. Let's do it down here where we have more room, shall we? 1.41 times 10 to the -5th equals whatever we have defined as our silver concentration at equilibrium squared, multiplied by whatever we have defined our sulfate ion concentration to be at equilibrium. That's where students get mistaken. And yes, we still square it. The 2 gets used 2 times. It's twice the concentration, and it's squared. So simplify that to 1.41 times 10 to the -5th equals 4S cubed. Now we simply need to solve for S, and we have our answer. Oh gosh, don't I divide by 4 first? Divide by 4. Divide by 4. I think that's right. I just forgot. Oh, let me look here. I didn't write it down, but I'll make sure. 1.41 second E -5 divided by 4 equals raised to the 1/3 close parentheses equals. Nope, it looks like we need to raise it first. Okay, clear. 1.41 second E -5 raised to the 1/3 equals divided by 4 equals. I didn't get any of those. That's frustrating. 1.52 times 10 to the negative second. Let's see, 1.41 second e negative 5 divided by 4 equals raised to the yeah, I got it. So we divide by 4, and that's going to give us, sorry guys. That's going to give us, when we divide by 4, it gave us 3.525 times 10 to the negative 6 equals s cubed. Okay, now what I do is I take this 3.525 times 10 to the negative 6, and I raise it to the 1/3. And that equals S, and S equals 1.52 times 10 to the negative second. So look at the molar solubility in relation to KSP and in relation to the other elements KSPs. We actually have a pretty high molar solubility. I think, okay. Now, that's S. That is the molar solubility. They also asked to have it in grams per liter. So if we just go moles per liter, change our moles of silver sulfate to grams of silver sulfate, and we will have grams per liter. I actually have the molar mass right here. It is 311.9. And my friends, that gives us 4.75 grams per liter is the solubility. Okay? All right, I think we have some more practice problems. We don't! Yay! Yay! Okay, great. See you guys later.